So last time we were discussing mean anomaly. So let's define the mean anomaly first. So this is the actual elliptic orbit. And the blue circle is actually a hypothetical circular orbit. Okay. Let's imagine that a fictitious satellite uh, goes around the Earth in this orbit, hypothetical circular orbit. Okay, and this satellite has the same orbital period as the real satellite. Okay, and the radius of the circular orbit is the same as the semi-major axis of the real orbit. Okay, then uh, the angle that the imaginary satellite makes. So this is the point of perigee, denoting P, because the Earth is here at this focus, and this is apogee. Now the mean anomaly M is the angle that the imaginary satellite makes with the major axis. So this is the major axis. This angle is mean anomaly. Okay, it is denoted as M. How about the real satellite in the real orbit? Let's say at the same point in time. So this has to be defined at a particular point of time. We have defined all other ecumenic parameters at the time of equivalence, right? So mean anomaly is also given at the time of equivalence. Okay. How about the real satellite? Where is it? Let's say the satellite is somewhere here. Okay. And it makes, so we join the satellite with the focus. Okay. And this angle is denoted as mu, and it is called true anomaly. this one. This is the angle. Okay, and the angle that the real satellite makes with the major axis is actually the true anomaly. Okay, actually we are interested in finding the true anomaly, but in the orbital parameters we are given mean anomaly. And yesterday I noted that the orbital parameters or Keplerian parameters are given at a particular time called time of ephemeris, and the broadcast parameters are valid for 2 hours. So every 2 hours, in case of GPS and IRSs, every 2 hours they are changed by the satellite. So all the sets are uploaded by the control segment and then they are broadcast by the satellites. The satellites change the parameters every 2 hours. So within this 2-hour period, um, we need to use these orbital parameters and determine the satellite position in the orbit. And definitely the satellite position changes in the orbit right as time passes, correct? So suppose we have been given these orbital parameters at some time TOE. Satellites will broadcast them at some particular time over that 2-hour period. Okay, so this time remains fixed over that 2-hour period. But if we want to find the satellite position, so time of ephemeris TOE is this time. Now we want to find satellite position at some other time, right? Because we have this 2-hour window, and within this 2 hour in the any time we can pick and find the satellite position. It's a T, and T is not equal to TOE. Now how can we do it? Uh, so there are ways to actually determine the other orbital parameters if the perturbations are also broadcast by the satellite. If the perturbation parameters are not broadcast by the satellites, then we have to take the same semi-major axis, eccentricity, longitude of ascending node will change over time. That is at a particular time. So depending on Earth rotation, we can calculate the longitude of ascending node. Okay, argument of perigee. If no perturbation information is provided by the satellite, we will take the same argument of perigee over the 2 hours. But how about the true anomaly? True anomaly will change because the satellite is moving in orbit, right? So actually, we are interested in finding. We need to find mu at t using m at TOE. So this is our objective. Now, why we do not have mu at TOE? So we'll understand that. Now, see this blue satellite, the imaginary satellite goes in a circular orbit, meaning it has the same angular velocity, right? Because it is moving in a circular orbit, same angular velocity. And what is that angular velocity? Angular velocity, let's denote it as n. It has a name, okay? And the orbital period, it's let's say is t. The orbital period of the real satellite, because the imaginary satellite has the same orbital period as that of the real satellite. We can use that to find the angular velocity of the imaginary satellite. So n is the angular velocity. It is also called mean motion. And since the imaginary orbit is a circular orbit, it is given by 2 pi by t. The t is the orbital period. And for the imaginary satellite, we are doing it for the imaginary satellite and it is constant. So, given m at TOE, how can we find m at t? We just need to extrapolate it. So, m at TOE, and then how much the satellite has moved in the orbit, the imaginary satellite has moved in the orbit over the time difference between t and TOE. So for that we have to consider the angular velocity or the mean motion and multiply it with the time difference, so t minus TOE. Since the angular velocity is constant, we can simply do the multiplication with the time difference and add that to the mean motion at TOE to get the mean motion at t. To get the mean annually at t. So we can easily extrapolate the mean anomaly to some other time. And this is why we actually use mean anomaly in the ephemeris, not true anomaly. We could not have done this extrapolation for the true anomaly. Okay. Now our objective is to find the true anomaly at t. Okay. We have got the mean anomaly at t. How can we find the true anomaly at t? So to do that, we also require an intermediate parameter called eccentric anomaly. So eccentric anomaly actually allows us to go from the extrapolated mean anomaly to the true anomaly at t. Okay. So let's define the eccentric anomaly. So this is the real orbit. This is the point where the Earth is, and let's say this is where the real satellite is in the real orbit. And this one is the circular orbit using which we found the mean anomaly. Okay. Now, from the point where the real satellite is, we draw a perpendicular line, extend it, and find the point where it intersects the imaginary circular orbit. Don't think that the imaginary satellite is at this point. No, not necessarily. It will not be. Okay, so we have just taken the real satellite in the real orbit, extended a vertical line, perpendicular line from that point, and find the point where it intersects the imaginary orbit. Okay, and then we connect this point of intersection with the center. Okay, this angle is eccentric anomaly. Okay. Now we have extrapolated mean anomaly. Our next task is to find the eccentric anomaly at t. Eccentric anomaly at t is given by this formula. So we know this one, we have extrapolated the mean anomaly, but we need to solve this equation iteratively to find the eccentric anomaly. Fortunately for a near circular orbit, with 2-3 iterations we can find the eccentric anomaly. So we assume that the initial E is the same as the mean anomaly at T. Okay, and then we put this E naught here and calculate the new E. Okay, and then we put that new E on the right side and recalculate it. So this way we do 2 to 3 iterations and find that the difference between the new E and old E is much less than a tolerance. And then we say that the solution has converged. So for a near circular orbit, like the one for GPS or IRNSS, um, the solutions converge with 2 to 3 iterations. Okay. Uh, then after obtaining the eccentric anomaly, we use this relation to find the true anomaly. Okay. Now here, after finding the true anomaly, there might be a sign ambiguity. Okay, that sign ambiguity can be resolved by in one of the two ways. Either you can find both cos and sin mu, and then from there you find in which quadrant. So there are 4 possibilities, right? The real satellite can be one of the 4 quadrants, right? So using cos and both cos and sin, we can resolve that sign ambiguity. Or another approach is to see where the imaginary satellite is. Okay, and the real satellite will be in the same quadrant. Okay, so this way we can get rid of the sign. So the imaginary satellite and the real satellite, they will be in the same quadrant. We have 4 quadrants. Okay, so either by using the sign of cos and sin mu, we can find a quadrant, or using the mean anomaly, we can find out in which quadrant the real satellite will be. So using the mean anomaly, easily we can find the true anomaly at some different time step. If we had been given the true anomaly at TOE, we could not have extrapolated it so easily to some other time step. This is the reason why the mean anomaly is given in the orbital parameters, because here the objective is that the user will decode all the orbital parameters, Keplerian parameters from the signal, and then find the satellite position in the orbit for different time of interest, okay, within that 2-hour window. Because we know that to find the range or determine the user position, we need satellite position. Satellite position is a function, the range is a function of satellite position. So we need to know satellite position to find the user position, right? And this is how we can find the satellite position using the orbital parameters. Now here we just found the true anomaly, okay? But when we put the satellite position in the range equation, we actually need the satellite position in ECA. Okay, there is an algorithm that does that. So it basically takes the orbital parameters, okay, extrapolated orbital parameters, and then find the ECF satellite position. So we started with the orbital parameters at T naught. If perturbations are given, we apply all the perturbations. If not, we just take the other 5 parameters. Longitudinal ascending node can be extrapolated using our rotation. And then we extrapolate the mean anomaly, find the true anomaly at the time of inquest. And then we can use these extrapolated orbital parameters to find the satellite position initially. We will not get into that algorithm. Um, but just note that there is an algorithm. If you know it from some other class, it's fine. There is a standard algorithm and it's not much difficult, which does this easily. So we're basically going from one frame to another. So we can take the orbit as a frame. Okay, we can define x and y axis in the orbital plane. Okay, and then from there we just need to go to the EC frame. Okay. Any question? Any question?
No.
Okay. Next, we are going to talk about GPS signal structure. So, we have talked about the satellite orbits, GPS and IRNSS orbits. Next, we are going to talk about the signal structure. First, we will talk about the GPS signal structure and then IRNSS signal structure. GPS offers two services. Standard positioning service, SPS, and precise positioning service. GPS. SPS is available to all. Okay? Okay, it's basically for uh, civilian users. Then PPS is for the military, US military. And other Department of Defense, DOD, authorized users. Okay. So we do not know about the PPS signal structure fully. Okay. Some of it is completely unknown. Some is partly known but encrypted. So we'll not discuss about PPS here. We'll mainly concentrate on SPS, standard positioning service. In SPS also we'll not talk about all signal structures. There are different components. We are going to talk about the most basic one, but we'll note what the other components are briefly. Okay. Now the signal, the transmitted signal, from satellite I at time t can be mathematically represented as okay, here there are other components as well, but they have complex structures and I like on new satellites, block 2 or M onwards, they have other components as well. Okay, we will not write this here. Now this P represents signal power. We defined signal power in a previous class, and we also discussed how, given a signal, how we can find the signal power. So just use the sinusoidal signal, sine or cosine function, and use that formula to find the signal power. You will see that the amplitude is actually given by this square root of 2p. Okay. So P is the signal power, and this first component we call quadrature component, and the second one we call in phase. Okay, there are other components as well. They are also put in quadrature and in phase, but we have just shown the simplest one. Okay, quadrature and in phase. Then C is the pseudo random code. Last time we discussed pseudo random codes, right? So they allow us to uniquely identify a satellite, and pseudo random codes are also used to determine range to satellites. Then D is navigation data. We also talked about navigation data, right? The FCA is the carrier frequency. We know that any GNSS signal has three basic components: code, carrier, and data. Right? Code, pseudo-random code; carrier, which carries pseudo-random code and navigation data from satellite to user; and then navigation data contains information, various pieces of information about the satellite. Now, in this representation, the expression that I have given on the previous page, C and D, code and data, take values of plus minus 1. So they will be either plus or minus, plus 1 or minus 1. Okay. There is another representation where we assume that they take 0 and 1. So plus 1 is changed to 0 and minus 1 is changed to 1. So this representation is also possible, okay? And they are equivalent. But for mathematical computation, this plus minus convention is useful because we can just do simple multiplication. With 0 1, it will not be simple multiplication. But after some time, we will establish the equivalence between them. Okay? Now let's assume that they take values of plus and minus 1. We already know that the carrier is the sinusoidal electromagnetic wave, synchronized oscillation of electric field and magnetic field that can travel even in a vacuum. And this electromagnetic wave actually carries code and data. Right? So this is the carrier. Then we have the pseudo-random code. So here we assume they take plus minus. So let's say this is plus 1, this is minus 1, pseudo-random code. And then we have navigation data. Each pulse of code is called chip. And in case of navigation data, each pulse is called bit. Okay, number of chips in a second is chipping rate. Right, we briefly talked about this. This is chipping rate. And why the code is called pseudorandom? Can you tell me why the code is called pseudorandom? Did we discuss this in the class? At least tell me whether this was discussed in the class briefly or not. Why the code is called pseudorandom? So nobody knows why the code is called pseudorandom. Was this discussed in the class? You can't even tell whether it was discussed or not. We have the project presentation next week, next Friday.
Yes, ma'am, it was discussed.
So can you tell me why it is called pseudorandom if it was discussed? So nobody can tell me why it is called pseudorandom?
Ma'am,
Yes.
bits have
Yes.
not any fixed pattern, so they are random. That's why it's called random, pseudo-random.
If it is completely random, we will call it random. Why do we call it pseudorandom?
Because the input is deterministic, so but the output has random variables, so it is pseudo random.
From where did you get that? Did we say that in the class that the input is deterministic? If input is deterministic, how can the output be random? Did we say that in the class, Ajika? That input is deterministic and output is random, that means pseudo-random? Or you are guessing something?
No, ma'am, it is my guess only, ma'am.
In yes. Shujit,
Yes, ma'am.
yeah, so why is it called pseudo random?
Ma'am, I think due to the code period.
What is that code period? What is code period? Hmm? You mentioned some code period. Can you define what code period is?
Means period of the random code.
The period of the random code means what? So what is changing and what is a period means something is repetitive, correct?
Right. Yes, ma'am.
What is repetitive here? You tell me what is repetitive. You said period, right? So something is repetitive. So tell me what is repetitive.
Pulse, series of pulses.
What? Widths of pulses?
No, series of pulses, ma'am.
Series of pulses. Okay, so you mean the values, plus minus?
Yes, ma'am.
Yes. So basically it appears random but it is actually not random. It has a pattern that repeats after a certain time and that time is called code period. Okay. So every code period we have the same pattern repeating. But if you see the series of plus minus 1 over a short period of time, you will find that it has some random pattern. You will not be able to make out that it repeats sometime. This is why it's called pseudo-random. Okay. Ajita, have you understood?
Yes, ma'am.
So you will have plus minus 1 series of plus minus 1. It's not that plus will be always followed by minus 1. So you can have multiple pluses, plus 1s and then one minus 1 or multiple minus 1 then 1 plus 1. So there is a series of plus minus 1s and the series actually repeats after some time and that time is called code period. Okay. Um, Now the carrier is transmitted in 3 bands, 3 frequencies. L1, which is 1575.42 megahertz. L2, 1227.6 megahertz, and L5, 1176.45 megahertz. Okay. Now the L band, which spans 1 to 2 gigahertz, is reserved for satellite navigation. Okay, all the different constellations that we mentioned earlier have carrier frequencies in this band. Only exception is IRNSS, which has an S band signal. Okay, so IRNSS is the only exception. The S band can also be used, but L band is preferred. S band has other issues, and that is why, partly because of that, ISRO is planning to include another L band signal for new IRNSS satellites. Now, the current satellites transmit carrier in 2 bands, L5 and S. Okay, L5 I have given here. But S band has some issues. Okay, it is close to Wi-Fi, so there is a chance of getting interfered with Wi-Fi signals. And then, so what do I mean by that? The receiver is meant to pick up signals in that band, right? S band. But if Wi-Fi signals are also transmitted in the same band, then there is a chance that the receiver will pick up that signal as well, and that will actually introduce error in the final output. Okay. Moreover, there is a large separation between L5 and S band. Okay, so antenna design becomes complicated. It's difficult to have a small antenna that can cover both L5 and S. Because ISRO is planning to have L1 band news and message satellites. Now, why the L band is chosen for carrier? Why the L band, or it applies to S band also? So basically, why we have this band for satellite navigation? Now this is done for some reasons. Now, if you pick some signal at a low frequency, say a few kilohertz, then they cannot penetrate the ionosphere. See, satellites are far away, right? Some 20 to 30,000 kilometers away. And satellite signals are transmitted, they need to travel through the Earth's atmosphere and then reach the receiver. So this means they also have to travel through the ionosphere, the layer of charged particles in the atmosphere. It is seen that low frequency signals cannot penetrate the ionosphere. So they get reflected back. So if you have a transmitter on the ground that transmits signals at few kilohertz, then the signals will get reflected from the ionosphere and then come back to the Earth. Okay, so they cannot. Now, in case of satellite, what will happen? They will be reflected back to the satellite. That is not the objective, right? We need something that can penetrate the ionosphere. This is why we cannot go for a very low frequency signal. Now, if we have a high frequency signal, say tens of gigahertz, then the disadvantage is that signals get attenuated. by rain, clouds, etc. This is why the dish antennas cannot pick up signals when it rains heavily. Signals get attenuated and you will not get signals. But if you want to use satellite navigation for so many different applications that we discussed earlier, you cannot afford to have signal outage because of bad weather. You need something which will work in all weather conditions. And it is found that the L band and part of S band suits that purpose. So they can penetrate the ionosphere, they can penetrate the ionosphere. Rain, clouds, fog, etc. So we basically get signals in all weather conditions with this band. This is why we go for this one for satellite navigation. Okay. Now GPS has different types of pseudorandom codes. The most basic one is called course acquisition, and in this class we are going to discuss things for this only, this course acquisition. This is the basic, the simplest one. CA code. Okay, it's chipping rate, 1.023 megahertz. Code period 1 millisecond. Okay, so this is the simplest of all codes, and we are going to talk about the receiver operating principles for this code only. Okay, then there is another one called P code. This is 1 week long. 1 week long means this is the code period. Okay. Shipping rate 10.23 megahertz. Now P code is actually meant for authorized users, okay, for precise positioning service. So P code is actually encrypted. The encrypted P code is called PY code. So this is the encrypted P code. Now only if the user has a key to decrypt this code, they can use the P code, the advantages of P code. Okay. Otherwise, they can do processing, but they will not be able to retrieve the code. Without the code, they have to do processing. That provision is also there, but it will not be as accurate as the one where the user can decrypt the P code, the PI code to get the actual P code. So these three codes were present in all the satellites from the two codes, course acquisition and PY code. They are present from all the satellites, present in all the satellites from the beginning. Okay. Now, new designs introduced new codes. Okay. For example, block 2RM, we defined these blocks yesterday. 2RM onwards, whenever a new code or new signal is introduced, it will be carried in all the subsequent blocks. So 2RM onwards, we have additional civil codes, L2 civil long and L2 civil moderate. Then block 2F onwards, we have I5 and Q5. We need not bother about this, just note that there are additional codes. Okay, it's not just that the signals have only one code. That should be the takeaway message for you. Later we'll form a table where we'll show these different blocks and the corresponding code and data for comparison purposes. But don't worry about all this. Just need to get the message that there are multiple codes and they have some purpose to serve. It's not that simply these different complex flows were introduced. They were introduced for certain reasons, okay, to address vulnerability basically. Similarly, there are different versions of navigation data. Legacy navigation data is present in L1. Okay, so this is for L1 then. It's 50 bits per second data stream. So in case of navigation data, one pulse is called a bit. So in the case of legacy navigation data, there are 50 bits in a second. Okay, now what is transmitted through the navigation data? So from the navigation data, we get satellite ephemeris, orbital parameters, satellite clock error, from GNSS system time, then we get satellite health status, signal status, signal health, etc. Okay. So legacy navigation data is for L1 carrier frequency, then it is present from the first satellite on from the beginning itself. Then civil nav data was introduced in the L2 band for civil users from 2RM onwards, block 2RM onwards. Okay, so they have additional information that you do not get in legacy nav data. For example, you get additional orbital perturbation parameters. So any receiver that can decode this civil nav data from L2 carrier frequency will be able to apply these additional corrections to the orbital parameters and therefore gets more accuracy. If a receiver does not have the capability to process L2 band, then it will not be able to take advantage of this. Okay, so block 2RM onwards, civil nav data was introduced. So 2RM onwards means 2RM, 2F, 3, all blocks of satellites have civil nav data in L2 band. Okay. Previous satellites did not have any nav data for the civilian users. Okay. Then another civil nav data called D5 is there for civil use. From 2F onwards. In the L5 band. So the military can actually use both L1 and L2. Okay. We want dual frequency capability because later when we'll talk about the ionosphere, we'll see that if we have dual frequency signals, if the receiver can process dual frequency signals, it can eliminate the ionospheric error. The ionospheric error actually has a dominant contribution to the civil measurement. So if we can eliminate the ionospheric error, we can improve the accuracy to a great extent. This is why capability for dual frequency processing is desirable. Now, in earlier design, they provided the dual frequency capability only for the military. Civilian users did not have. Later, from 2RM onwards, they introduced dual frequency capability for the civilian user as well, but in the L2 band. Now the problem is that aeronautical users cannot use the L2 band because the L2 band is used for other purposes, other navigation aids for aeronautical users. So just for the aeronautical users primarily, they introduced the L5 band. But other civilian users can also take help of the L5 band. Okay? So L2 band cannot be accessed by all civilian users. Okay? Aeronautical users cannot use the L2 band because other navigation aids already designed to operate in those bands, so they cannot use L2 band. For them specifically, the L5 band was introduced, but of course other civilian users can also use all three bands, okay, L2, L1, L2 and L3. Later we'll put all these different codes and data in a table for different blocks of satellite. In fact, we'll just do one more thing and take a break, 5-minute break, and then after that we'll do that table, and then you can show me your homework problem. Okay. Earlier I said that this plus minus 1, this actually this plus minus 1, this we are using in our representation for this way. So here we assume that they take plus or minus 1. C and D take plus and minus 1. Now let's quickly see how the modulated carrier looks. So basically when we multiply this C and D to the carrier, this is the carrier, right? Cos and sine, basically two components, in phase and quadrature phase components. And then when we multiply C and D this way to the carrier, this is called BPSK modulation. Okay. If you are not familiar with this, don't feel intimidated. There is nothing great about it. So you are just taking the sign plus or minus 1 and you are multiplying that to the carrier. That's all you are doing. This is called BPSK modulation. So when we multiply carrier and data this way, we are actually modulating or changing the carrier. Code and data, if we multiply this way, we are actually modulating the carrier, and this is in this case we have the simplest form of modulation called BPSK modulation. So let's quickly see how the modulated carrier looks. Let's say this is the unmodulated carrier. This is unmodulated. Okay, then we have code and data, right? So instead of code, I'm sorry. One chip will have multiple carrier cycles. So I'm just showing 3 cycles, but don't think that it is only 3. Ajita, you are following, right? Ajita?
Yes, ma'am.
Okay, so I'm just assuming that there are only 3 cycles in a chip. This is one cycle, second cycle. I'm not putting it. This is one chip. We assume that only 3 cycles are there. And then let's assume that the second chip has -1 for understanding purposes. So this is 1 cycle, 2 cycles, 3 cycles. We'll just show it for 2 chips. Okay. So this is, let's say this is code. Next we'll draw carrier. Navigation data. Next will be navigation data. Let's assume that the navigation data is negative up to this. Okay, at the satellite level, they are all synchronized. Okay, code, carrier, data, they are all synchronized. Okay, they end together, they start together. Any changes, they are all synchronized. Okay, of course, the navigation data will be much longer because 50 bits per second, you can imagine, right? And then the carrier has a frequency at the gigahertz level, whereas here we just have 50 bits. So it is much longer, but here for representation purposes, I have shown only few cycles. Now, next we want to draw the modulated carrier. So we'll draw only for up to this point. Okay. Now just see, you multiply code and navigation data. Code over these 3 cycles, code is +1 and navigation data is -1. So this is -1 and this is +1. Right? So plus 1 minus 1 will be minus 1, correct? So you need to multiply minus 1 to the carrier. Ajita, so following, right? So if you multiply minus 1, what do you have to do? You just need to reverse this, correct?
Yes, ma'am.
So we just need to reverse the whole thing. So here we had plus, so that will become minus. Right? Right? Okay, now over this, what do we have? We have minus 1 for code. We also have minus 1 for navigation data. So minus 1, we get plus 1, right? Which means we need to multiply plus 1 to the unmodulated carrier, right? The carrier will remain unchanged over this, correct? So we need to actually put the same carrier. So this is how the modulated carrier will be. After we do BPSK modulation. Here we are assuming that they take values of plus minus 1. The code and data take values of plus and minus 1. Now what if instead of plus 1, if we assume that we take 0 value and then minus 1, we take plus 1. So this representation is also possible. Generally for mathematical computation we use plus minus 1 because that is easier, but 0 1 representation is also possible. Okay. Now if we are using 0 1 representation, then we have to do modulo 2 sum. This is modulo 2 sum. What is modulo 2 sum? Basically, for modulo 2 sum, modulo means you have to do find the remainder. So remainder of the sum when divided by 2. So use sum the two quantities and then divide the sum by 2. Find the remainder, and that remainder is actually the result. This is what modulo 2 sum is. Okay. Now let's quickly establish the equivalence between the two. So if we want to do modulo 2 sum of code and data, we will write this. When we are using 0 1 representation, if you are following 0 and 1 representation, then we need to write this. If you are following just plus minus 1, then we just multiply the two. Simple multiplication. So this is simple multiplication. Now both the representations are possible. So it's important to understand both. Okay. So for example, if you look at the ICD interface control document, where detailed structure, civil signal structure is given, they follow this modulo 2 sum notation. So it's important to understand the equivalence between the two. Whether it is plus minus 1 or modulo 2 sum, you basically get the same end result. Let's quickly establish that equivalence with the help of a table. Here we will do modulo 2 sum. So the operation that we will want to perform is modulo 2 sum here. Okay. And therefore we need to use 0 and 1, 0 and 1. And we will write the results. Then we will also use simple multiplication. For simple multiplication, we need to take +1 and -1. So let's do the simple multiplication first. Simple multiplication, +1 we get 1. So what we are doing, +1 we are multiplying, we get 1. -1 +1 we get -1. +1 -1 we get -1. -1 when we are multiplying we are getting +1, right? Now we know that we need to, if we want to go for 0-1 representation, we need to replace 1 with 0, -1 with +1, and this is what we should get if we are doing modulo to sum, correct? So let's see if we are getting that. 0 plus 0 divided by 2, remainder is 0. 0 plus 1, it is 1. When you divide it by 2, the remainder is 1. 0 plus 1, 1 divided by 2, remainder is 1. 1 plus 1, 2, divided by 2, remainder is 0. Now just compare this result with the right hand side table, and you just compare with the values that I have written within brackets. You see the same values, 0, 1, 0, 1, 1, 0, 1, 0. So they are actually equivalent. Simple multiplication has to be converted to modulo to sum if you are using 0-1 notation. Okay? This is modulo to sum. And we see from this table that they are equivalent. Right? So that's that proves the equivalence between the two. Let's complete the table and then we'll take a 5-minute break. After the break, you can show me what you have done for the homework. Okay. What we are going to do next is we'll form a table and quickly show different codes and data that are available in the 3 bands, L1, L2 and L5. Here we have 2, 2A, okay, and then 2R. Then under each band we have in phase and quadrature phase. So I'll write just I for in phase and quadrature phase. Note that I is for PPS. Okay. In L1 and L2. And Q for SPs, civilian use. L5 band is for civilian use. Okay. L5 is for civilian. Military does not use L5. Military can use L1 and L2. Okay. Now the I has, since this is for PPS or military, it has D for legacy nav data. Okay, so modulo to sum of Py and D that is present in the in phase component. In phase is sine. In the earlier representation, we use sine for in phase and cos for quadrature phase. We are actually interested in SPS, okay, but we will also note the PPS part to the extent possible. Not everything we will be able to note, but for PY part, I think we can easily do that here. Then this one has CA modulo to sum legacy nav data. Then PPS has for the in phase component now. For these blocks, there is no code and data for the civilian users in the L2 band. So the civilian users only had this quadrature phase in the L1 frequency. In the L2 frequency, L2 carrier, there was no code and data for the civilian users, meaning the civilian users could not use this L2 band. But for PPS, precise positioning service, we have both L1 and L2. In the L2 band, the control segment could choose which of these can modulate the carrier, whether it is PY plus data or simple PY no data, or it can also be CF plus D. Okay. So this was the signal structure for these blocks. Then 2RM, 2F and 3. All of them had new signals introduced, new code and data introduced. In the L2 band for civilian users. Okay, now this also has new code and data for military. M stands for military. And the modulation here is not BPSK modulation. For this M code and M nav, it is not BPSK modulation. Okay. This was there earlier also. Notice the change here. See, for these blocks, the control segment decided whether they would use PY or CA. If they had used CA, the civilian user could have used, but generally they use PY for precise positioning service. Okay, generally this band was not available for the civilian users. Then what they did, they removed this CA and D from this block onwards in the in phase completely, because they put additional code and data for the civilian users in the quadrature phase. So they used this RCA, no data, or earlier I mentioned that a new code was introduced in the L2 band for civil users. So these are the ones. Okay. Now you will not understand this notation, so let me explain this a little bit more. So I have written L2CL. So basically this is the civil moderate code. And DC is civil lab data. Okay. This one has a chipping rate 511.5 kilohertz. Okay, and it is 20 millisecond long. Just compare this with CA code. CA code is 1 millisecond long. And this one is very long code. I think I mentioned about this. Yes, civil long and civil moderate. This I mentioned from 2RM onwards. The civil long code, for this the chipping rate is again 511.5 kilohertz, and this one is 1.5 seconds long. Again, just compare this with CA code. CA code is just 1 millisecond long, whereas this one is 1.5 seconds long. And how they are transmitting the two? So they actually do modular to sum of L2 CM and DC. Okay, and this modular to sum alternates with L2CL in time. What does it mean? So you just take L2CM and DC, find the modular to sum. You will have a series of zeros and ones. Similarly, you get series of zeros and ones for L2CM. So first you take one chip from this one or one pulse from this one, and then the next pulse will be taken from this one. That's how they alternate in time. This is how they have actually put the code and data for the civil user in the L2 band. Okay. I'll quickly put that table again because I could not accommodate all the blocks here. And this is the last one. This one here, I'll just write psi 5 with this. This was introduced from 2F onwards in the L5 band for civil air purposes. Again, this is a new code. This is the D5 nav data that I mentioned here. D5 nav data I mentioned, and I5 and Q5 ports I mentioned. So they are introduced in the L5 band only 2F onwards. Okay. Here I cannot show it differently because the blocks that I have shown 2RM, 2F and 3. So in the L1 and L2 band they have this code and data, all of these blocks. But 2RM does not have this one in the L5 band. That's why I put 2F onwards. All the blocks have this I5 and D5 for L5 band. And this is only for civil use. Okay. I'll just write what was introduced from 3A onwards. So in block 3, additional code they added for civilian users. Now this one is not BPSK modulation. I'll also write the chipping rate, L1C chipping rate. Chipping rate is the same as CA code, and port length ten milliseconds. For this also the same L1C. Okay. Here I'll write the details for I5. I5 has a chipping rate of I5 and Q5. Okay. Here also ports. Chipping rate is 10.23 megahertz, just like P code, and they are 1 millisecond long, just like CA code. Okay. So these are all different codes and data that they have added with modern design. Now you may ask why we require such complicated design. And all the new signals do not have BPSK modulation. BPSK is the simplest modulation where we just multiply plus minus 1 with the carrier. Okay, so they do not have even BPSK modulation. They have more complex modulation scheme. Now you can ask why we are actually varying the chipping rate and code period. So you can see that the chipping rate, we want either higher chipping rate or higher code length. Either we are going for higher chipping rate or we are going for higher code length. If possible, we want to increase both. For example, in case of PY code is 1 week long and 10.23 megahertz is the chipping rate. So what is the rationale behind going for higher chipping rate and higher code length? Higher chipping rate allows us to determine the range measurements more accurately. And higher code length allows us to track weak signals. Okay, so we can receive weak signals. I will not use the word track at this point because you may get confused. So, this is right. But it is a valid use. It seems you are not familiar with tracking at this point. And right, receive weak signals. We want to receive weak signals, we want to improve accuracy, and it can be shown that if we increase the chipping rate, we can have better accuracy. If we have a higher port length, we can actually receive weaker signals. Okay, so these are the motivations why we actually have so complicated design. So that's all about the theory class. We'll take a 5-minute break, and then you can show me what you have done for the homework. It is 12:38 now. Let's have a 5-minute break. And then we'll resume our discussion at 12:43. Yes. Who will explain the problem? Who will explain the problem? I have received Shujit's solution. Krishna and Ajita, have you done?
Ma'am, I tried, ma'am, but I didn't get the Kalman filter problem.
Which one you have tried? Show me what you have done.
Can you see my screen?
Yes.
First of all, I tried the MMSC, the problem, the question, whatever you have given with MMSC method, and I got the estimate value as 2.919. And then I tried the same problem with WLS method.
Hmm.
Then in this, after doing all the calculations, I got
See,
the
what is your H matrix? H is 1. Okay. It's a column of 1.
because
Okay.
yes,
Hmm.
ma'am. W covariance of nu.
Hmm.
So I got as identity matrix. Then the formula what we learned
Hmm.
has been applied, and then I got the estimate value as 2.836.
Okay.
Then the LMMSC method, linear estimate
But
method.
you did not calculate the covariance. You should also calculate the covariance, right? Error covariance. That formula was also derived in the class.
Okay, ma'am.
Yes. Okay.
I'll
So
do that.
whenever you need find the estimate, you should also find the associated error covariance.
Okay,
That
ma'am.
will tell you the quality of estimate. Okay. Then
Then using the third method, uh, again found the matrices, ma'am.
okay,
Uh,
tell me the matrices here. Okay, you have ones. Okay, and then find identity matrix for the covariance. Okay, after that. Okay.
then afterwards, again,
Okay.
since estimate is CY,
Hmm. You need to find C.
hmm,
Okay, HP H transpose, then plus W
I
the
mean I did
inverse.
step by step. Then
Okay.
this to find this inverse, I used MATLAB, ma'am. Then I
Okay,
got
fine.
this
Okay, then.
matrix after from MATLAB. Then I
Hmm.
got estimate as this. So from three methods, these are the estimate values what I
So
got.
I think you made some mistake for MMSC.
Okay.
It will be 2.7 something.
Okay. I'll look into it now.
Okay, for Kalman filter, where are you stuck?
Kalman filter, actually, to be honest, I'm not able to uh, clearly understand, how to proceed forward and all. So I was going through this,
No,
ma'am.
but why didn't you? No, you here you will get the derivation, right? So
From
at the
the
class note.
notes also,
Yes.
I've gone through the class notes also,
Hmm.
but I think I have to read it again, or I'm not so confident with this.
You have to start with some initial guess, correct? Do you have the class note with you here? Can you quickly
Hmm.
open the class note?
Yeah, okay. Here,
Hmm.
uh, wait, ma'am, I'll show. State space model, right.
So you need to
So,
first formulate the state space models. Have you done that? That should be the first step. In this case, it is simple, correct? You just
it
need
is already like it is given as y equal to x plus nu.
yes.
So the
And for the state transition model, what will you use?
x
You show me the state
x dot
transition model here. You show me what I wrote for the state space
state space,
representation.
this one represented
Okay,
x
so
is
what is
ax
A?
plus du.
What is A? In your case, that for that example problem, what will be A? It is a constant, right? X is a constant.
Yes, X is a
Right?
constant.
Then what will you write for A?
The one
Yes.
column matrix of ones.
Why column matrix of ones? You have just X, one X, right? X is a
Okay,
parameter.
A is a
What you are
constant.
estimating here, what you are estimating, X is a constant. It is a single quantity,
Hmm.
right?
Okay, ma'am. Huh.
Then what will A be?
Then A would also be 1.
A will be 1. So you just have xk plus 1 is equal to xk. Uk is not there because that is what the model is. Xk plus 1 is equal to xk. And wk is also not there because you don't have any information about it. So you just assume it to be 0. Your model is xk plus 1 is equal to xk.
Okay, ma'am. Then this is given.
So Q is 0, the covariance of the process noise is also 0. Although this is not the right way to implement the Kalman filter, because if the process noise is 0, if you pay attention to the Kalman gain that you will calculate with each measurement, you will see that it is decreasing. So Kalman gain decreasing means the filter is actually not giving much importance to the measurements. It is actually relying on the state transition model more, because you have said that the process noise is not there. So this is not how the Kalman filter should be implemented, but for that problem we need to do that because there is no process noise. Okay.
Okay, ma'am.
So now that you have A is equal to 1, Q is 0 because there is no process noise. H is also equal to 1 because you will
1.
be not, yes, 1 because you will be processing one measurement at a time. It is recursive in nature. So you need to process one measurement at a time, right?
Mm.
Okay.
Okay, ma'am.
So will you be able to do that now?
I'll try, ma'am.
Yes, please do that because
Okay, ma'am.
estimators are included in the syllabus and in the project presentation I can ask questions about the estimators. Okay.
Okay, ma'am.
So rest is straightforward. Once you form the state transition model, you identify R and Q matrices. Rest is straightforward. You just need to use the equations recursively, the way you did for MMSE. That is also a recursive way of doing it, right?
Yeah,
You
yes, ma'am.
using one measurement at a time.
Mm.
Because the formulation was like that in that problem. In the Kalman filter also, you will process one measurement at a time. Okay?
Okay, ma'am.
Yeah. So do it, and then you need to also derive some conclusion, correct, from the result.
Comparing the
Yes, comparison results.
yes, ma'am.
Yes. Okay. So complete that.
Mm. Okay,
Yes.
ma'am.
Uh, who will come next? Krishna.
Yes, ma'am.
Can you quickly show what you have done?
Yes, ma'am. Is it visible?
Yes.
Ma'am, this is the first question.
But
I'll,
did you correct? Did you correct the mistake with
yes,
MMSC?
yes, ma'am. Yes,
Last time
ma'am.
you had a
Actually,
mistake.
uh, ma'am, actually, in previous question, this
Hmm.
MMSA, I was not using inverse, like 1 by sigma v square plus 1 by
Okay,
sigma
so
x square.
what is the estimate you got? Let
Right
me
now, I'm
see.
at 2 point something. I have not
Show me what it is. Because Ajita showed 2.9. So what value did you get?
ma'am, actually,
Have you
I did.
completed till the end? You did not go to the end.
No, ma'am, actually, that was the only mistake. I did this in rough
But then what is the end result? What
2.9.
estimate did 2.9
2.9.
you got? Just show me. I don't think.
I was getting 2.9
You are
only.
getting 2.9.
Yes, ma'am. In WLS, it was 2.8.
I don't think WLS. No, no,
Okay.
no. Something is wrong. Because Kalman filter and MMSC will give identical values.
I will check it
WLS
again.
will not be close. Okay. MMSC and Kalman filter, LMMSC also will be closer to the truth. WLS will not be. Something is wrong. Okay, then show me. Show me what you have done for LMMSC.
This one is LMSA. So this is the measurement equation. And
Next, let's go to the Next.
Same I'm giving 2.7.
Okay. And how about the error covariance? You also did not find the error covariance. You should always find the error covariance along with the estimate. Without error covariance, you are not getting any idea about the quality of estimate. So whether it is a column filter or any other estimator, you should also find the error covariance. Okay?
Yes, ma'am. I will try it.
What is there to try? You have the expressions were derived. What is there to try? You just need to put the values and do the
These are the
calculation.
linear equation, so
Oh,
put that and getting result. This is not non-linear. This is a linear equation. That's why I'm directly putting the
oh. So
in this.
what is there to try? You just need to put the values. That only I'm not understanding. What is there to try? You said you need to try. What will you try? I'm not getting what you will try. What do you want to try?
We have to find the estimate using all these four and five methods. So actually, this derivation is already there.
Hmm. Then what will you try? You said you will try.
When I
You just
solved these equations again on the rough paper.
error covariance was already derived in the class, right?
Yes,
For
ma'am.
LMMSC also it was derived in the class, linear minimum mean square. Was not it derived in the class? The error
Yes, ma'am.
covariance?
Yes,
Then
ma'am.
you just need to use that, correct?
I
And
don't
find
know.
that.
That was a question. That was also a question.
That only I am saying whenever you are finding the estimate, you should, what is the objective of the homework? To improve understanding, right? And the error covariance actually gives you an idea about the quality of estimate. That's why I'm
Yes, ma'am.
asking you to find the error covariance. In this case, you will just have one value because it is a single quantity. X is a single scalar, right? So the error covariance will give you an idea about the estimators, which estimator has lower error covariance or do they have comparable error covariance. This actually helps you to compare the estimators. Whenever you are asked to compare results, error covariance is important. How about the column filter? You have not done column filter?
I
Only
have done.
MMSC? Then
No, ma'am. I've done this one also. So
show
actually,
me column filter.
this y is equal to x plus n. X is a scalar quantity. So this is
Why
a
did you
measurement.
assume q is equal to 1? Who told you that you have to assume q is equal to 1? You don't have any q only here. No process lines.
I have assumed a model also. Xk plus 1 is, I'm assuming a is 1 and q is 1 and r is 1.
You cannot assume q is equal to 1. No information is given, moreover it's a perfect model. When the model is perfect, it is told that x is a constant. There is no ambiguity about it. It's a perfect model, so q will be 0. There is no process noise. This is just an example. Ideally, there has to be a process noise, however small it is. But here we assume that we know the model perfectly. If we know the model perfectly, we will not put any process noise. You have been told nothing about process noise, right? You just told it is a constant. So you
And I
assume q is
also
equal
said
to 0.
there is always a discrepancy between
Yes,
mathematical.
but in this case there is no discrepancy, right? You have been given the correct model. So you have to pick q is equal to 0. You know x is constant. Q is equal to 0 has to be used. Then
What about r?
R is given. Why are you
R is,
assuming R? R is given. What value of R will you take from the problem statement?
sorry,
Does not it say anything about the noise, measurement noise?
sorry, ma'am. Yes, ma'am. R is actually talking about the error, measurement error.
Yes. What is that?
Next, I have applied this for first
What
data.
is R? What is R in the problem?
R is 1 actually.
R is 1. It is
Yes.
given in the problem. Okay, next. Scroll down, scroll down. Krishna? We can't hear you. I think there is some issue with his network. Okay. I'll quickly share the screen and show what.
Yes, ma'am. Sorry, ma'am. That was the internet problem.
But you did not show me what you did till the end.
Yes, ma'am. I'm showing again.
Okay, then quickly show me because I also have to see what Shujit has done.
Is it visible?
No. Yes. Show me quickly.
This
Scroll
one is
down.
for first data,
Okay.
and
First
finally
measurement.
I'm getting 2.8268.
See,
Perfect.
I'm telling you one thing. The best way you can verify is you know that column filter is minimum mean square error. And there is no nonlinearity here. So whatever you are getting with minimum mean square error, the same thing should come with the column filter also. Same thing, error covariance will match, estimate will also match at every point. With every measurement, you should get the same. This is a way you can cross check. Okay? I'm telling everyone. This is the best way you can verify whether you have done it correctly or not. Because column filter is a minimum mean square error. And you have a linear problem, so minimum mean square error will also give a linear estimate. Column filter also gives a linear estimate. You should get actually identical results. At each step, you will get the same estimate for both MMSE and column filter because both are solved using one measurement at a time. So you can easily compare. Column filter will give you one estimate. MMSE will give an estimate using the first measurement. You should verify whether both have the same estimate and error covariance. If they have, then you know that you are doing it correctly. Otherwise, you have made some mistakes somewhere. Okay? Ajita, you understood, right?
Yes, ma'am.
Okay, let me quickly see what Shujit has done.
Ma'am, excuse me, ma'am.
Yes.
Ma'am, can we assume R is 1? It is already given in the question, ma'am. In the column
It is,
filter, R.
uh,
Is it okay? Can we assume R is 1?
if it is given in the problem statement, what is there to assume? It is already
Yes.
given, right?
Yes, ma'am.
Then why do you want to assume something which is already given?
Sorry, ma'am.
R is equal to 1, it is given clearly, correct?
Yes, ma'am.
Okay. Okay, so Shujit, can you quickly explain what you have done? Okay, good. You have written down all the things in one place. Shujit?
Yes, ma'am.
Yes, so you have, okay, you have put the measurements and the corresponding measurement model metrics. Okay, fine. You have done intermediate calculations. Okay. And then finally, this is what you got. This 2.7. Have you done the
Yes, ma'am.
calculation? You got
Yes.
2.7?
Yes, ma'am.
Okay, I think Ajita also got 2.7. Krishna, what did you get? 2.7 for LMMSE? Linear minimum mean square? Krishna? Krishna is not there? Krishna? Okay, Ajita, you got 2.7, right? For linear minimum
Yes,
square?
ma'am.
Okay.
2.701.
Yes. Okay. For Kalman filter, what did you assume, Shujit? What is Q?
Q is 0, ma'am. Is
Okay,
written
very good. Okay, Q is 0. Where did you write Q is 0?
up, up.
Okay, Q is 0. Okay, very good. Fine. Okay, so you have incorporated the prior information as initial guess. Okay. So, okay, so Ajita, you are getting some idea how you need to do the intermediate calculations using one measurement at a time. So, this is the guess. It is given in the problem statement. The prior information has to be actually used as the guess, initial
Okay.
guess. Okay, so he has taken 0 because the prior distribution has 0 mean
0,
and
4.
variance.
Variance 4.
Yes.
Yeah.
So this is 0 and this is 4. Okay, and then he has used the Kalman filter equations and found the error covariance and estimate. Okay, and
Okay,
this
ma'am.
has to be repeated. So for the
For the
next,
next.
yes, it has to be repeated. And then finally, what did you get, Shujit? You got 2.701. Okay, and 0.1904. And for minimum mean square also, yes. See, in his case, both are matching. So they should match. Kalman filter and minimum mean square error, they will match. Each step has to match. Then you will know that you are doing it correctly. Okay. Shujit, anything else you want to say? That you have not done two things. You have not found the error covariance for linear minimum mean square error. You should also find the error covariance for weighted least squares, which you did not do last time. Okay, you did not find the error covariance for weighted least squares. You should do that. Whenever you are asked to compare two estimators, you should consider error covariance also. Okay.
Okay.
And you also did not say anything about the comparison of the estimators. That is also missing in your homework. Okay. You should conclude about the estimator's performance because you have been
Okay.
asked to compare the estimators, right? You did not do that.
Okay.
Simply do not leave this at this point. You also need to conclude what you have obtained. Okay, which
Okay.
estimator is better. So how will you find which estimator is better? You do not know the truth. So the best way to find which estimator is better is to find the error covariance. Whichever has error covariance, since you have no other information available, whichever has least error covariance can be taken as the best one. And you also need to see the relative values of the estimates, whether they are close or not. Multiple estimators, if multiple estimators give close values, then you can, from there also you can say that okay, these estimators are probably giving correct results. Okay, so if one estimator is away, another two estimators are close, then you will know that okay, two different estimators giving similar results means this is closer to true. So this type of comparison you should do. Okay.
Yes.
Okay, fine. That's it. You can leave now.
Thank you, ma'am.
Yeah, I
Thank.
asked you something. Krishna, you did not answer at that time.